Right now, beneath the floor of the ocean, two machines the size of apartment buildings are grinding toward each other through solid rock, and when they meet, they need to be within 2 centimeters of each other, or the whole thing is worthless. Why this tunnel exists? Zhoushan is an island cluster off China's eastern coast. Productive, economically significant, home to one of the country's largest offshore industrial zones. And for most of its history, it has been connected to the mainland by ferries and a series of bridges that work fine for cars but are completely inadequate for high-speed rail. Ferries are slow and weather-dependent. Bridges in this location face a specific problem that makes adding more of them impractical. The shipping lanes above this stretch of water carry vessels so large that any bridge spanning them needs clearance heights that make construction enormously complicated and typhoon vulnerability a genuine concern. A tunnel solves all of that at once. It sits below the shipping lanes, below the weather, below every surface problem that makes bridges in this location difficult. The payoff is direct and measurable. A journey that currently takes over an hour by car or ferry becomes 30 minutes on a high-speed train. China has spent the last decade building 45,000 kilometers of high-speed rail, more than the rest of the world combined. Connecting islands and coastal zones that rail cannot reach by land is the logical next step, and the Gintang Undersea Tunnel is the most ambitious version of that step attempted anywhere. The machines. To build a tunnel 16 kilometers long with more than 11 kilometers of it carved directly beneath the seabed, China deployed 2 tunnel boring machines named Dinghai and Yanghe. Each one weighs around 4,000 tons, roughly the equivalent of 8 fully loaded Boeing 747s. The spinning cutterhead at the front that grinds through the earth is nearly 15 meters across, which means the opening it carves is large enough to accommodate twin high-speed rail tracks with all the infrastructure those tracks require. What makes these machines genuinely remarkable is not just their size, but what they do while they move. As the cutterhead grinds forward, the machine simultaneously removes the excavated material, installs precast reinforced concrete rings that form the permanent tunnel walls, and injects grout to seal everything into place. The tunnel is being built continuously as the machine advances. There is no pause and build phase. It is one continuous operation happening deep under the ocean floor. The deeper problem these machines face is that the ground beneath the seabed is not uniform. Over the course of the tunnel, the machines encounter 28 transitions between different geological conditions. One stretch is solid granite. The next is soft clay or sandy soil that behaves completely differently under the pressure of the machine and the water above it. Engineers addressed this by adding water injection systems to prevent clay from clogging the cutter blades, reinforcing the pressure systems to handle the crushing water load at 78 meters of depth, and installing 20,000 sensors throughout each machine to monitor conditions and adjust torque, thrust, and cutting speed in real time every few meters. The precision problem. Here is the engineering problem that makes everything else look straightforward by comparison. One machine starts from the Ningbo side of the strait and digs nearly 5,000 meters. The other starts from the Zhoushan side and digs over 6,000 meters. Somewhere in the middle, deep under the ocean, they are supposed to meet. And if they miss each other by even a few meters, the project does not work. You have 2 separate tunnels that go nowhere and billions of dollars of investment that produces nothing. The compounding error problem is what makes this so technically demanding. A deviation of just 1 degree at the starting point, something essentially invisible at the beginning of the dig, translates to dozens of meters of misalignment by the time the machine has traveled several kilometers underground. Traditional GPS positioning is accurate to within a few meters at best, which is fine for navigating a car but completely useless for threading 2 4,000-ton machines through solid rock toward each other from opposite ends. China's solution was to link both machines directly to 6 dedicated Beidou navigation satellites, their domestic equivalent of GPS, combined with a real-time kinematic positioning system that pushes accuracy down to within 2 centimeters. Every few meters, the machines transmit their exact position in 3-dimensional space. The system compares that position to the planned route, calculates any drift, and sends micro-corrections back to the steering mechanism. If a machine is 1 centimeter off course, the system catches it and corrects it before that 1 centimeter becomes 10. When Dinghai and Yanghe finally met deep under the seabed, the total alignment error between them was less than 20 millimeters. 2 centimeters on a tunnel stretching over 11 kilometers through variable rock and ocean floor geology is an engineering result that most people in the field of tunneling describe as almost implausible. What happens to the machines? Once the two machines meet, there is an obvious logistical problem. They are trapped. There is no exit ahead of them, no way to drive them back 11 kilometers through the tunnel they just created, and no realistic method of lifting 4,000-ton machines from 78 meters below the ocean floor. So Chinese engineers do something that sounds drastic, but turns out to be the most practical and structurally elegant solution available. They dismantle the machines from the inside out. The drive systems, the hydraulic components, the cutter heads, every expensive reusable part is extracted and hauled back through the tunnel by hand. What remains is the outer steel casing, the massive cylindrical shell that housed all the machinery, and that shell stays in place permanently. It becomes part of the tunnel wall. The machines that built the tunnel become structurally embedded in the tunnel itself. They do not just complete the job, they become the job. Construction on the Gintang tunnel began in late 2020, with tunneling ramping up significantly through 2024. Excavation is targeted for completion by the end of 2026, after which approximately a year of finishing work begins. Track laying, electrical systems, ventilation, lighting, safety infrastructure. The tunnel is scheduled to open in 2028. The bigger picture. The Gintang tunnel connects Ningbo to Zhoushan, and that is genuinely useful on its own terms. But engineers and analysts looking at this project from a wider angle see something else happening here. The Taiwan Strait, at its narrowest point, is approximately 130 kilometers wide. That is 8 times longer than the Gintang tunnel. The water is deeper, the currents are stronger, and the geological conditions are considerably more complex. A tunnel across the Taiwan Strait would be without question the most ambitious infrastructure project ever attempted by any country in history. Nobody builds something like that without first proving the technology works at smaller scale. The Gintang tunnel proves that China can navigate 28 geological transitions under active ocean floor, achieve sub-2 centimeter meeting precision across 11 kilometers of underwater tunneling, and manage the full construction and engineering lifecycle of a high-speed rail tunnel at depths that have never been attempted for this kind of project before. Whether the Taiwan Strait Tunnel ever gets built involves political, economic, and diplomatic dimensions that go far beyond engineering. But from a purely technical standpoint, the Gintang tunnel is the proof of concept. China has now developed the machines, the navigation systems, the geological adaptation techniques, and the operational experience to attempt something of that scale. Most countries have built 1 or 2 undersea tunnels in their entire history. China treats them as sequential projects in a continuing program of capability development. The Hong Kong-Zhuhai-Macau Bridge included a nearly 7-kilometer undersea section completed in 2018. Gintang opens in 2028. Plans for further projects already exist. 50 years ago, a high-speed train running at 250 kilometers per hour 78 meters below the ocean floor was science fiction. 20 years ago, it was theoretically conceivable, but economically absurd. In 2028, you will be able to buy a ticket for it and eat a sandwich on the way. 2 machines, 11 kilometers of ocean floor, 2 centimeters of precision. Drop a comment telling us whether you think the Taiwan Strait Tunnel gets built in your lifetime. Check the end screen right now for more engineering breakdowns sitting there, waiting.